Welcome, Praveen Tipnis.
Okay, in the morning we saw how the structures could be built seismic resistant using prescriptive codes. Thank you. Using prescriptive codes as well as performance based codes. But what happens to an elevator which is there inside the structure? That's what is being addressed now in NBC 2016. And let's see very briefly what are the provisions that are to be made in case of a lift to make it seismic resistant. Okay, this is the map of India which is showing seismic zones, and you will see that about 54% of the land gets covered under the earthquake prone zone. So, with such a kind of thing that we have a seismic activity, we have to have definite consideration for elevators as well, because otherwise the tall buildings may survive the earthquake, but people might get stuck in the elevators or they may not be available. So elevators is a very important part of any high rise, so it has to be done in accordance with the codes so that it is available uh, for people as a service. And main important part is about the man trap, and the whole aim is to avoid man trap situation. So when we have earthquake resistance, I think it's very important first to detect the earthquake early enough. So fortunately, we have uh, in any earthquake situation, we have primary waves which are coming much earlier than the secondary waves, which are really damaging. So primary waves are faster and they travel in the direction of travel. The motion is like compression, and they are not damaging. But secondary waves, which are perpendicular to the motion, direction of motion, they are really damaging. The seismic detection system detects both horizontal and vertical motions, and what we do is detection system will detect primary waves, and it will signal the lift controller about the impending earthquake. So what is the effect of earthquake on elevator equipment? In elevator we have mainly car, counterweight, guide rails, machine, controller, speed governor, tension pulley, etc. These are the major assemblies of any elevator system. And here, uh, what happens is basically the car, which is heavy, and counterweight, which is equally heavy, they are subject to the acceleration due to earthquake. So they exert enormous forces on the guide rails, and there is a danger that either car or the counterweight might come out of the guide rail, and if the elevator is still in motion, then there is a possibility that there will be a severe accident. Then we have flexible elements in the elevator system like ropes, which are main ropes, compensating ropes, the cables, traveling cables, uh, etc., which are which get swayed during the earthquake. And we know that there are several snag points in the elevator system. For example, elevator guide brackets or the screw heads that are projecting in the shaft. There is always a possibility that uh, all these cables, traveling cables or the ropes might get entangled with the snag points. So this snag point protection is a very important aspect of the elevator protection in the seismic resistance lift. Next is the possibility of overturning. The For example, if there is a huge machine, when it is acted upon by the acceleration due to seismic activity, there is a possibility that the whole thing may turn. So this possibilities there for lift machine, lift controller, tension pulley. So all these assemblies, which are heavy assemblies, pulleys, they may get overturned. So we have to protect these elements from this kind of phenomena. So as I said, seismic resistant lift, the main aim, first aim is to avoid man trap situation. So what are the essentials? Uh, Basically, when we start designing, we should know what is the acceleration for which we should design the system. So what is the force that is coming on guide rails will be decided by the mass of the car, the counterweight, and the acceleration acting on that. And this acceleration is dependent on ground acceleration, the soil behavior, importance factor, etc. And there are other factors as well. So what's important is that by considering all these factors, the structural engineer has to specify what is the acceleration that the lift designer should consider in case of earthquake for protecting the lift equipment. Now, from the lift guidelines, if this acceleration is more than 1 meter per second square, then only there are the provisions get applied. Otherwise, for less than 1 meter per second square acceleration, you don't need any special provisions. As I said earlier, the protection of snag points, uh, this requirement is there only for buildings which are bigger than 20 meters or higher than 20 meters. So for less than that, you don't need any special protection for snag points. Because of the typicality of the traveling cables and the ropes of getting swayed. Uh, there could be various methods of preventing the entanglement of wires. That is by the uh, wires, or it could be entanglement bar, or even wire mesh. They are used, and these are all to be done at the design stage. So whenever the elevator is designed at that point, all these factors will be taken care of by the layout engineer, and he will specify which points what protection should be given. There is a possibility that there may be some rope guides which could be used for guiding the ropes, so that the idea is that the sway should be limited. Similarly, when there are compensating chain or ropes, there should be guide in the pit. All what we are trying to do is to limit the sway to minimum so that there is no entanglement possible later on. Now here are some guidelines as to what mass should be considered. In case of car, it is specified that the car weight plus 40% of the rated load should be considered, and in case of goods lift, it should be 80% of the rated load in addition to the mass of the car. There could be additional retaining devices to be used for cars and counterweight so that they do not come out of the guide rail and cause severe accidents in case of an earthquake. This is the representation of a guide rail section and the retaining device, and how the force into a direction to be considered for designing the car and the guide rail systems. Here is how the situation on the left hand side. We have the normal clearances with the retaining device or guide issue, as the case may be, with reference to the guide rail blade. And in case of earthquake, you will see that the gaps have increased, and still there has to be some minimum overlap of the retaining device with the guide rail blade, and that has been specified as minimum 5 millimeters. So in case of a worst acceleration, when the car hits the guide rail or the counterweight hits the guide rail and they are likely to bend, even the supporting bracket or the supporting beams could bend. So overall structure has to be seen, what all things are contributing to the deflection, and then we have to see that minimum 5 millimeters engagement is kept so that the future accidents are avoided. Here is a guideline about the stress level, and of course we are allowed to little bit go on a higher stress in case of earthquake, but that's design parameters. So we have already seen that all these equipments have to be protected. In case of power failure, automatic rescue device is compulsory in seismic resistance lifts. So that, because normally earthquake means generally there will be a power outage. So to avoid man-trap situation, the automatic rescue device has been made compulsory. And of course, the ARD cannot override for basic safety other functions, that if and only if all the electrical safeties are in place, then only the car should move. In case if the lift is in inspection operation or if it is in electrical emergency operation, the rescue device should not take over. And of course, the fireman's lift, if it is in fireman mode, the rescue device should not operate. The seismic detection system specified for this type of application is like this. Now, as per NBC 2016, this seismic detection system is compulsory if your design acceleration is more than 4 meters per second square. And for less than 4 meter per second square, it is kind of optional. So, the detection system should be able to operate all times when the lift is available. Its trigger level should be at least 1 meter per second square. Frequency response has to be from 0.5 to 10 hertz, and the system response time shall be less than 3 seconds. That means the moment it senses the primary wave and the lift goes in seismic mode cannot be more than 3 seconds. It should have an automatic test system to see that the whole system and the controller are interfaced together and they are working. And there has to be a manual reset so that in case the device operates, it's only by manual operation that the lift can be put back to service. So upon activation of the system, all calls will get cancelled. No new calls are registered. If the lift is in motion, it will stop or reduce in speed and try to move in direction which is taking the car away from the counterweight, and then it will go and make a safe landing, open the doors and shut down. In case of manual lifts, it will be delocked and the lift will be shut down. So the aim is to avoid injuries, man-trap, oil leakages. Now NBC 2016 is very close to EN 8177. This is the European norm for protection of elevators from seismic activities. Now both EN as well as NBC, they don't envisage any elevator service in case there is a seismic activity and the system is triggered. However, American code allows reduced speed service provided the counterweight displacement switch has not been activated. That means the counterweight has not left the guide rails. Now this is the most important thing from practical point of view. If you compare the seismic zones as defined by NBC and as defined by ASME code, because ASME code is what is generally prevalent in the industry, you will first see and notice that the zone numbers are not identical. So if we say that, let's say for example, Mumbai zone is zone 4, and if we try to specify, I want elevator system to be as per ASME zone 4, that's not the thing. It cannot be, because that American zone 4 is quite heavy. So what has to be compared? This has been compared with the scale and MSK 464. These are more or less comparable, and these are the levels, that is acceleration levels to be considered. So finally, what I would like to say is that we must go by the design acceleration specified by the structural engineer, and then arrive at the exact thing that we want to specify for an elevator. Let's not confuse the zone numbers from Indian and American. That's very important. So, thanks a lot.